We tend to define the world by its stability. The rigid panes in our windows and the cups on our tables are the definition of a solid. But that rigidity is not as permanent as it looks. Many stained glass windows in medieval cathedrals share a peculiar physical trait. The glass is noticeably thicker at the bottom than at the top. The common explanation is that glass is not a true solid, but a supercooled liquid. The theory suggests that over hundreds of years, gravity has been pulling the material downward, causing it to sag in a slow, centuries-long flow. If this theory holds, then the rigid glass in our everyday lives is actually in a constant state of transition, and the materials we rely on for structure are slowly melting away. To understand how these windows actually behave, we have to look past the architecture and down to the atomic level. In a traditional solid, atoms lock into a repeating geometric grid. But glass is different. Its molecular arrangement is chaotic, mirroring a liquid. This is an amorphous solid. The molten material cooled so fast that atoms couldn't form crystals, trapping them in liquid-like positions. This arrangement leads to a question. Can a material that looks like a liquid on the inside actually flow like one on the outside? Because an amorphous solid is unique, it behaves differently than any standard crystal or liquid. Verifying if it moves requires looking at the math of resistance. Physics uses viscosity to measure how much a material resists flowing. Water has very low viscosity. Room temperature glass has a viscosity so high it is nearly immeasurable. This slide from an MIT lecture on amorphous materials calculates the timescale of that flow. For fused silica glass to deform by just 10% under its own weight, it would take roughly 1.5 million years. The physics suggests the atoms aren't going anywhere on a human timescale. If the glass isn't flowing, we still must account for why these windows are physically uneven. The answer lies in the crown glass process. Glassblowers spun molten glass into large, flat discs. Centrifugal force made the edges thin, while the center remained thick. Workers cut rectangular pieces from these uneven discs, purposefully installing the thicker ends at the bottom for stability. The warped appearance of cathedral glass isn't a result of the laws of physics. It is the result of a specific historical manufacturing technique. To see how glass truly changes, we have to look past the 800-year history of cathedrals and into the deep time of geological epochs. These are lunar glass particles brought back by the Chang'e 5 mission. They were formed by high-energy asteroid impacts and have sat undisturbed on the moon's surface for millions of years. Over these vast timescales, the glass undergoes structural relaxation. The atoms very slowly shift, moving toward more stable, lower-energy positions. In the long term, glass doesn't melt or turn into a puddle. Instead, it becomes denser and stiffer. Given enough time, the material becomes more stable, not less. When we return to our own human perspective, we see a world that appears entirely static and unchanging. We initially saw the unevenness of old windows and assumed they were melting because our perception is limited by the speed of our own lives. Solid is a relative term. The glass around us isn't sagging, it's simply relaxing on a timescale so vast that from our perspective,